So today we're going to start, probably won't get through all of it. We're going to start section 7.7 over hyperbolic functions. And let's see if I can get my video pinned on my screen. There we go. Okay, so hyperbolic functions will probably be new to most of you guys. They don't come up very often, but it is important that we know what they are and how they're related, at least a little bit, to the trigonometric functions that you are probably quite familiar with. So let me just tell you what hyperbolic sine and cosine are, and then we can go from there. So these hyperbolic functions, we use the same kind of notation as sine and cosine, except we're going to put an h on the end for hyperbolic. And this one, hyperbolic sine, is e to the x minus e to the negative x over 2. So it's not a totally new function. It's just a combination of exponential functions that we already know about. And then hyperbolic cosine, which we'll use the same kind of notation for. So the regular cosine with an h tagged on the end. It's the same as hyperbolic sine, except there's a plus sign in between the two exponential functions. Like so. Okay. So I guess I should mention, usually if you're talking about hyperbolic sine, you'll say something like sinh instead of, saying the whole word out, hyperbolic sine. And hyperbolic cosine, you'll just pronounce how it looks, cosh, instead of saying hyperbolic cosine. So before we get any further, I want to look at a graph of these two functions. And we'll just use our handy graphing tool on the web. Switch over to that. Let's see, here we go. And these functions are actually built in to this calculator. And they're also, if you have like a TI-84 or an 83 or something like that, these functions are also built into those. So this is what hyperbolic sine looks like, or sinh, this red curve here. So it looks maybe a little bit like an x to the third power function, except it doesn't totally flatten out at the origin. And if you also compared them, you would see that this function increases a lot faster than the x cubed function. And then we can graph the hyperbolic cosine, otherwise known as cosh. And this looks a little bit like a parabola. It's not exactly a parabola because it gets much steeper. If I zoom out, you can see how steep it gets. It almost looks vertical as you go way up. And the red function, the hyperbolic sine, you can see also almost looks vertical. To get the blue one out of the way. And we can graph the blue function by itself. See, so zoom way out. They get really steep because they're exponential, or they're related to the exponential functions. Okay, so we need to go back to the notes next, unless you guys have questions over the graphs. So just like the trig functions, the other hyperbolic functions are going to be defined in terms of sinh and cosh. Just like, tangent is sine over cosine. And they actually work exactly the same. So hyperbolic tangent, or tanh, is hyperbolic sine over hyperbolic cosine. And then cotangent would reverse that, since it's, 1 over tangent, except now we're talking about the hyperbolic version. So it's cosh over sinh. So the nice thing here is that since you already know how sine and cosine work and all the other trig functions, you can kind of work similarly with hyperbolic functions. So secant is 1 over cosine, so sech, hyperbolic secant, is 1 over cosh, the hyperbolic cosine. And then cosecant is 1 over sine, so hyperbolic cosecant is 1 over sinh, hyperbolic sine. So those are the basic definitions, and I suppose we could go and look at some graphs of those as well before we move on, unless I start dropping things, which would make that a little bit more difficult. Okay, so let's just graph in a few more. So maybe hyperbolic tangent, which is the green curve here. So it almost looks like it has asymptotes, horizontal asymptotes. If you just look at the graph. And then we can do hyperbolic secant, which has this kind of a mounded shape. And then the coversions. So hyperbolic cotangent. This looks like the standard hyperbolic curves, but not exactly. And then, let's see, what are we missing? Hyperbolic cosecant would be this red curve, which looks fairly similar to the hyperbolic cotangent. And we should also maybe graph in a hyperbola, which is maybe a word that you haven't seen in a while. This is just an example. And we can get some of this other mess out of the way. So a hyperbola is something like this. Let's see, I don't want to talk too much about them, but you've probably seen functions like this, or implicitly defined functions like this: y squared minus x squared equals 1. Maybe back when you were in your algebra class in high school. And they're related to these two lines, or this particular one is related to these two lines that I'm about to graph in. Make those dotted. So you can see the shape of this curve looks like it's approaching the values of these two lines, y equals x and y equals minus x. And if you look in your textbook, or if you do some Googling or look at Wikipedia about the hyperbolic functions, you can see a few of the ways that the hyperbolic functions are related to this shape, or this kind of shape, the hyperbola. But we're not going to focus too much on that, like the geometry of it. We're just going to primarily use them as a source of new integrals that we don't know yet. And that's where they show up in real world problems. So these functions, even though they seem really weird, they do show up in actual physics problems and engineering problems as integrals or solutions to differential equations. And I put one example on the homework where these might come up in a real world problem, in a real world engineering problem. But before you get to the homework, of course, you have some more to learn. The next thing I want to talk about are some useful identities. These are fairly similar to the cosine, excuse me, the trigonometric identities. I said cosine because I was about to write cosh. So the first one looks a lot like the Pythagorean theorem, except there's a minus sign in it. And of course, we're talking about the hyperbolic functions instead of the trigonometric functions. And then we have something that looks a bit like the double angle formula. So if I have a 2x inside of my hyperbolic sine, this works a lot like the regular sine function. We get 2 sinh times cosh. And then I think after I write these down, maybe we'll work through the first one just to see how the formula works. Let's see, and there's also a formula for cosh of 2x. This one is a little bit more different from the equivalent trigonometric identities. This one actually gets a cosh squared plus a sinh squared. And then the last one is this one. Cosh squared of x is equal to cosh of 2x plus 1 over 2. And this is also related to a trig identity, an important trig identity that we're going to be using a lot in chapter 8. Okay, but that's for later. Let's just work through right now how number 1 works. Do a short little proof. So what we're going to do is just start on the left-hand side and then work our way to the right-hand side. So hyperbolic cosine squared minus hyperbolic sine squared. And then we're just going to plug in the definitions for cosine, or hyperbolic sine and cosine. For the first one, we get e to the x plus e to the minus x over 2. And then for the second one, we'll get e to the x minus e to the minus x over 2. Okay, so you can see that these have a common denominator, a 1/2 that we can pull to the front if we wanted. And then we can just look at the numerators. We have an e to the x minus an e to the x on top. That'll give us nothing, a 0. And then we have an e to the x minus, let's see, we have two negative signs here. E to the minus x minus negative e to the minus x. Oh, excuse me. I'm of course getting way ahead of myself because I lost a minus sign, a square sign on both of these. We're actually going to need some more room. Let me just rewrite that out. So that is actually correct. Like so, and then we'll need to square everything out. And in order to keep things organized, from this first term, we'll get a 1 over 2 squared, and we'll also get a 1 over 2 squared from here. So in order to make things easier to read, let's pull that 1 over 2 squared, the 1 over 4, all the way out to the front. And then we can square out on the inside. And this would just be a FOIL sort of problem. So you would get e to the 2x, or e to the x squared. And then you would get 2 times the cross term. So when you multiply these two, e to the x times e to the minus x would give you a 1, because you subtract the exponents. And then you would get this one squared. So plus e to the minus 2x. That takes care of the first one. And then we'll also need to square out the top of this one. The only difference is the minus sign. And then the minus sign in front, of course. So we'll get e to the 2x minus 2 times 1. That's where that minus sign plays a role. And then plus e to the negative 2x when this gets multiplied by itself. So if you're not sure how all that worked out, it's a good idea just to write it yourself using the FOIL method. But now that we have it actually squared out, we can see what cancels. We have an e to the 2x minus e to the 2x, and then we have an e to the minus 2x minus e to the minus 2x. And the only things left over are the 1 over 4 in the front. And then we have a 2 minus negative 2. So we have a 4 left over from the inside. And this, of course, comes out to 1. So that's how you would work out the first of these rules that I wrote down, the first of the identities. If you wanted to work out the other 3, you would do it the same way. You would just start with one side of the equation and then start filling in the details like I did here. So rewriting hyperbolic cosine in terms of its exponential functions, and same for hyperbolic sine. And then trying to work through and simplifying or transforming in some way. Do you guys have any questions?
I have one question. Why was it 2 times 1?
Sure. So back on the FOIL method, I didn't write out all the details. Let's maybe come down here and I can fill in that missing bit. So remember, when you square something like this, you're really multiplying it times itself. And then we can write out all of this. We get e to the x times e to the x. And then e to the x times e to the minus x. And then the inner two terms, e to the minus x times e to the x. And then the last terms would be e to the minus x times e to the minus x. And what you have to remember when you're multiplying exponential things together, if they have the same base, you simply add the exponents. So from this term, you would get e to the 2x. This term, you get e to the x minus x, that's e to the 0. And here you have e to the minus x plus x, that's another e to the 0. And then here you have e to the minus x minus x. So that's minus 2x. And these two are both 1. Of course, e to the 0 is 1. So that's where the 2 came from. 2 times 1. Make sense?
Yes, sir. Thank you.
Okay. Good. Any other questions before we move on? Okay, so that wraps up this page, these identities. I think your textbook might explain a couple more of these, or you could work through the details yourself if you wanted to. What we're going to do, though, is calculus. We're going to move on to the derivatives of some of these functions. And we'll work through the derivatives of the first two here in class, and then I'll just tell you the answers for the derivatives of the other hyperbolic functions. So if you want to find the derivative of hyperbolic sine, you would go back to the definition. We know hyperbolic sine is e to the x minus e to the negative x over 2. And then we can just find the derivative here directly. So this division by 2, that's just a constant, so we don't have to worry about it. You could rewrite it in the front as multiplication, but I'm just going to leave it here. So we have to take the derivative of e to the x. That'll give us e to the x again. I guess we talked about that not too long ago. And then we'll need to take the derivative of negative e to the negative x. So we'll bring along our minus sign, and then we'll take the derivative. We'll pick up an extra minus sign from the exponent, like this. And then we still have that constant on the bottom that came along for the ride. So two minus signs make a positive sign. So what is e to the x plus e to the minus x over 2? Did we have another name for that?
Is it cinch?
You're close. We started with sinh. We ended up
Yeah.
yeah, I think that's what you meant to say. Yeah, so just like the derivative of sine is cosine, the derivative of sinh is cosh. So this first rule is exactly like the rule that you already know from trigonometry. Any questions over that derivative? No, okay. So let's do the derivative for cosh as well. And the only difference here is that we have a plus sign in between the two exponential functions. So when we take the derivative, we still have an e to the x, but then we'll pick up another minus sign here. So we'll get minus e to the minus x over 2. Do we have another name for this function? E to the x minus e to the minus x over 2.
Sinh.
It's sinh, right. So this is the point where cosine and sine differ from sinh and cosh. You should remember that the derivative of cosine is actually negative sine, but the derivative of cosh is positive sinh. So even though they work similarly to the trig rules, there are some differences. So I'm going to put a little note here that this is actually one of those. This is different from your trig rules that you already know. So you need to keep careful track of how they're related and how they're different, because that same pattern of differences and similarities is going to continue. So the derivative of tanh is sech squared, just like the derivative of tangent is secant squared. But then there's a difference when you take the derivative of sech. It's a little bit different from secant because there's a minus sign. But you still have sech and tangent, or tanh, excuse me. So this is another one of those little differences. But then koth or koth, or this one is a little bit more uncommon. This one is the same as the trigonometric version. I'll get the word out eventually. It does pick up a minus sign, just like the derivative of cotangent is negative cosecant squared. And then this one also gets a minus sign when you take the derivative of cosec, hyperbolic cosecant. Okay, so overall, extremely similar to the trig rules, but also with some subtle differences that you'll have to remember. So we could work out these rules for 3, 4, 5, and 6 the same way that we did these two. But we're not going to do that today. It might be on your homework. I can't remember if I assigned one of those, but you might have to work through one of these rules on your own. So if I was going to work this out, I would rewrite tangent, hyperbolic tangent as hyperbolic sine over hyperbolic cosine, and then use the quotient rule. Since you already know derivatives for sinh and cosh, you don't have to work through those derivatives again. You can just use the quotient rule to figure it out. Okay, so I think that's going to be our stopping point for today. Are there any questions here at the end of class?